Hey everybody, I'm back. I was wrong. We had another page of notes I wanted to do. In 11.5, we talked about skewed lines. This was actually 11.5D. We did skewed lines and we saw they were in different planes. I have this pictured over here. This is from section 11.5 in the book. Skew lines, they're not parallel and they lie in different planes. So if we want to find the distance between skew lines, this is what we can do. I use the same lines we used in 11.5D, where I had the great time saying T1 and T2. It was fantastic. So I've drawn our pictures similar here with L1 and L2. I use the vectors V1 and V2 being the vector components of these lines. And so if these planes are parallel, the two normals should have the same normal. They should be the same vector. So there I go ahead and decompose our lines into two parallel, or the 2 points and the two vectors. And so how can we find n if we have these two planes? I don't have a third point in each plane. What we can do is we know V1 and V2 are not parallel, but they are in the same plane. So we could make them, we could do it, since they're not parallel, we can cross them to find a vector that's orthogonal to both. And since V1 and V2 are in parallel planes, we should be able to get the same thing. So let's do n equals V1 cross V2. So that's what I've got going on here. I've crossed V1 and V2. 131 and 252, we cross them. 6 minus 5 gives us 1 in the I hat. Then we cover up J. 2 minus 2 is 0, so it doesn't matter that's minus 0. J is 0. And K is 5 minus 6, we're going to have negative 1. So our normal vector is 1, 0, negative 1. And when we see when we plug in T equals 0, of course, we get back our two initial points. What we're now to find the distance between these skew lines, all we got to do is find the distance between these planes. And in the last section, we learned how to do the distance between the two planes. Recall we did P naught dotted, or P naught P dotted with N. We took the value, the absolute value of that, and we divided by the magnitude of N. So let's find P naught P. We're going to do that in the second plane. We're going to use that as our plane. So that's what I'm going to do here. We already have N here. N is 1, 0, 1. We're going to use our 3, negative 4, 5 to figure out that's going to be our P naught P. So that's going to set up the vector x minus 3, y plus 4, and z minus 5 using this. Those get plugged into there, x minus x naught kind of thing. We have 1, 0, 1. So when we dot P naught with P, I get x minus, that's our equation. And if we simplify it out, x minus 3 and z plus 5, we're going to gather like terms, and I get x minus z plus 2 equals 0. This part on the left is our top part, D. And the x and the z we use is from the other plane, P1, because that's the point we're trying to find a distance to. So we're going to plug that in. Our x is 2, our z is 3. 2 minus 3 is negative 1. Plus 2 gives us positive 1. That's our top. And then the norm on the bottom is the magnitude of 1, 0, negative 1. So 1 squared, 0 squared, and negative 1 squared add up to 2. We've got the square root. So the distance is 1 over root 2. And so this is root 2 over 2 units. That's the distance between those two lines. As a recap, what did we do? We know that these planes are parallel, so the normals are the same. We found a normal vector by crossing the two vectors that live in the skewed lines, which come from these components right here, our T components. Those are right there. We crossed those to get N, which was here. And then we used our distance formula. P naught dotted with P, or not, sorry, not P naught dotted with P, P naught P dotted with N. And divided by the magnitude of N. That'll wrap up 11.6. That'll be done. Peace.